Hello, thank you for watching this video. I am Cecilia Curreli and I will be introducing WalkingDynamicsH36M, a benchmarking dataset for long-term motion and trajectory forecasting. This work is a joint collaboration of the National Institute of Informatics in Japan, the University of Tokyo, and the Technical University of Munich. Pose and trajectory forecasting considers the human motion as a combination of both the centered pose and the trajectory. The task consists in taking as input a motion sequence and output the corresponding future sequence. WalkingDynamicsH36M is the first benchmark for long-term 3D motion prediction. Long-term means that from the past 2 seconds, we aim to predict the next 4 seconds. 4 seconds into the future is a long time interval, and the farther we go into the future, the more the future becomes uncertain, since in real life, the same path can generate different futures. To be able to create a deterministic benchmark, we constrain the action to the motion of walking. We show that the dataset sequences are homogeneously distributed in the trajectory space, and so the dataset is suitable for probabilistic motion prediction. We introduce a baseline for the task, GradIN, a pure graph convolutional network with a recurrent encoder-decoder structure. With GradIN, we present a novel parameterization to encode the motion sequence into graph nodes. The body joints are centered and normalized around the hip, while the hip is expressed in terms of the absolute univector and magnitude. We evaluate GradIN also for short-term motion prediction on the social motion forecasting benchmark SOMOF. GradIN achieves competitive results even if it's not pre-trained on the AMAS dataset, like the 2 state-of-the-art models. For the task, we also introduce a simple algorithmic baseline, slide pose, showing that in this case, short-term motion prediction can be very well approximated by just sliding the last seen input pose. Here we can see a qualitative example. The performance of motion prediction is usually measured by the average Euclidean distance between ground to the prediction, the mean per joint projection error. MPJP has limitation while handling long prediction time horizon. For example, the score will be very similar for a sequence with low precision and low variance, or a sequence with high precision and high variance. We introduced 2 complementary metrics, MPJP pose and L2 trajectory. The first one considers only the pose centered around the hip in a pure pose prediction fashion, while the second one considers only the trajectory. Taking another reference joint as the hip does not significantly change our results. The experiment results show that SOMOFORM achieves the best results according to the absolute Euclidean distance MPJP and the trajectory error, while our model generates centered pose closer to the ground truth according to MPJP pose. By taking a look at the average bone deformation over time, we see that our model predicts much more realistic sequences. These insights are supported by qualitative evaluation. On the sample on the left and right, we see that SOMOFORM predicts a trajectory very close to the ground truth, but tends to degenerate into sliding towards the end of the sequence, since it was designed for short-term prediction. In the middle, we see clearly the bone deformation of SOMOFORM, while our generated motion looks overall realistic. WalkingDynamics and GradIN are available on GitHub. We hope you enjoyed our talk. Thank you for your attention.